We have seen this somewhere before. Like yesterday, and we called it the Laplacian. And what is this? This is the gradient of divergence. Which is number 3. So this, the gradient of divergence on its own doesn't mean anything. Remember we said it doesn't have a physical significance? But it becomes useful when we talk about the curl of a curl. Now suddenly, when it gets added onto a Laplacian, it gives us stuff. Okay, keep that in mind. Keep that in the back of your mind. We'll come back and revisit it in later chapters. Okay? Okay. Now, what is a Laplacian? A Laplacian is something that we will pick up from number 1. So I'm going to move back. Everybody look up. I am moving back to number 1. Okay? So let me explain 1 and 2. So pick a color.
Purple.
Purple. Do I have purple? Is dark pink okay? So I'm going to recall this, that color. And I'm going to continue this definition down here, because this is important. So del dot del of a scalar can be written as partial over partial x squared. Remember, it's a dot product of t plus partial squared over partial y squared t plus partial over partial z squared, partial over partial z squared t. And that is called del squared t, or the Laplacian. Please note the Laplacian of a scalar is also a scalar. So wrap your mind around that. The first derivative, which we called the gradient of a scalar, was a vector. Do you remember here? Right here? So the first derivative of the Laplacian with a scalar was a vector. Here, what we discover is that the second derivative of a scalar t is in itself a scalar. Okay? So the first derivative gives you a vector. The second derivative gives you a scalar. Just a number. Okay, now number 2 is left. The curl of the gradient. What is the curl of the gradient? Should I use, oh, can I use green for that? I'm going to recolor this one green. The curl of a gradient. Griffith says this always equals 0. So the curl of the gradient is always 0. And I think he proves it too, which we are not going to get into. But if you look it up, I think he does prove it. So you can say the curl of a gradient equals 0. And we're going to stop discussing that now. Okay, I want to also mention one other thing. These two, actually. So if I write this as del dot E, which was the gradient of a divergence, please note, these two are not equal. So you cannot write del dot E to be the same as del squared T or del squared E. So you cannot operate a Laplacian and make it a gradient of a divergence. Divergence of a gradient and gradient of a divergence are two different things, and they are not equal to each other. Please, please, please make sure you remember that. These two are not equal. So all of this stuff that Griffith does can now be reduced to this basic two things. Can I put them in a box? So summary. This is what I want you to remember. There are only two main kinds of second derivatives that we care about. Number one, the number one, which was the Laplacian, the del squared, which is very, very, very important. And number two, the number three equation, which was the gradient divergence, which is important, but not as important. And I think Griffith uses the word seldom encountered for it. And I think he also says something like, and you can also do third derivatives the same way, which will be the curl of the gradient, or the gradient of the curl, or all of those things that follow through. But he says, because they're not of any practical importance, we're not going to worry about it. But if you're interested in math and you want to be very careful and want to do those, Casey's already saying no, but if you want to do those, you can look at them and make sure that you understand them at your convenience. We will not do them in class. Okay?